Yeah, welcome everybody. We're very glad to have Hannes Matt here today, and he is going to talk about Banach gradient flows for various families of knot energies. So Hannes, please go ahead.
Okay, thank you very much for the kind introduction, and also thank you a lot for allowing me to talk here. Welcome everyone. I will now start my talk. So this is joint work with Daniel Steenebrügge, who is also here in the audience, and our supervisor, Heiko von der Mosel, supervises both our PhD studies from me and Daniel. And let's start. So today I will talk about Banach gradient flows for various families of knot energies. And I would like to start with a small introduction, explaining what the title means, what the words in the title say, and give a small overview of what has already been done. Then I will state our main result as gradient flows in Banach spaces, and then go on with the proof, which is based on the theory of curves of maximal slope and minimizing movements, which is basically a theory of gradient flows in metric spaces. So what are knots? A knot is an equivalent class of embeddings, so of closed curves in R3. We map the unit circle into three-dimensional space, and well, as curves or as functions, these two objects are different, but we would like to identify them with each other. And we say that two such curves are equivalent if there exists an isotropy of the ambient space R3 that transforms the one curve into the other. So broadly speaking, in an ambient isotropy, we are not allowed to cut a knot to let it self-intersect. For example, let this edge here pass through the other one so that we get another knot class. And we also do not allow pull-tight phenomena. Big questions in the theory of the knot theory, or the biggest maybe, is how to classify our knots. Can we give some quantities or some algebraic classes or whatever to fully classify our knots? And a smaller question is, which I will be mainly addressing in this talk, is how can we easily assign an arbitrary knotted curve to the class it represents? And to do so, Shinji Fukuhara in 1988 introduced the concept of knot energies. A knot energy is a functional on a space, a set of knots, and it assigns to each knot a number. And the goal is to let this number decrease so that the form of the knot transforms into a so-called, or what he calls a standard form. So why is this useful? First of all, it may be another tool to address the classification problem. For example, many of these knot energies have the property that below a certain energy threshold, not every knot class is present. So for example, here in this little picture, we have the unknot, the circle, the trefoil knot, but the figure 8 knot is not, it's not below this energy. And more importantly for my talk here is this other picture, starting with this trefoil knot, which is quite edgy, and letting it evolve following the gradient of this knot energy. It transforms into this standard form. So when trying to compare knots, we do not have, let's say, if we could manage to find a gradient flow for every knotted curve and know that this gradient flow in fact converges to the standard form, then we wouldn't need to compare curves, but could directly compare the standard form of these curves. So now I will give a couple of examples of knot energies. The Juno Hara in 1991 introduced the so-called Mergus energy, which is defined as follows. Given here, this is just a piece of a knot, so a part of the curve. And let's say we have 2 points, and on each of these points, we put a small electron. And then these two repel each other, and we get like a Coulomb potential. And this gives the energy, which is 1 over the distance between those 2 points. Well, this has a degree 2, a singularity of degree 2, and we are on a curve, so an object of 1 dimension. So this will always be infinitely high if we integrate it naively. So what he did was to take the finite part of this integral. Later, in 1992, he then introduced or generalized this Mergus energy, which, by the way, is called Mergus energy because the value it gives to this knotted curve is invariant under Mergus transformation. So if I take this gamma and apply a Mergus transformation onto this gamma, then the energy will stay the same. So in 1992, he generalized this energy by first of all rewriting it in this form here, and then replacing the 2's by alphas and introducing an integrability constant or parameter p. Another class of knot energy was proposed by Oscar Gonzalez and John Maddox in 1999, the so-called integral Menger curvature. In this case, we take, again, a curve, and this time we compare, or we let 3 points on this curve interact in such a way that, the energy is given by the inverse of the radius of the unique circumcircle passing through these points, and then raised to the power p. A little bit later, Simon Blatt and Philipp Reiter then extended this integral Menger curvature to the so-called generalized integral Menger curvature. What they did is to see that the radius can be written in this particular form here, and then they had the idea to decouple these 2 parts and replace this p with a q. Here we lose this nice geometric representation, so this is not anymore a radius of a circle. However, this comes with the benefit of having nice analytic properties, which were exploited to, for example, show that minimizers are smooth. So the next class of knot energies I would like to talk about was introduced by Paweł Strzelecki and Heiko von der Mosel in 2012, the so-called tangent point energies. This energy is the first of the 3 that is not symmetrical in the 2 points gamma x and gamma y. This should be a little y. So the energy is pointwise defined as the inverse of the radius of the unique circle passing through both points, but that is also tangent at the curve in this 1 point. So we can then integrate this pointwise density to get the tangent point energies. Again, Simon Blatt and Philipp Reiter extended this notion to generalized tangent point energies by again decoupling those two values and introducing the exponent q instead of p half, which it was before. Which again, we lose this representation as a radius of circle, but they get some nice analytical properties out of it. So what now we have seen some examples. I would like to talk in general what the knot energy is. In the introduction, I said that it's a map that associates to every curve a number. Here we want some little more structure. So we say that it's O'Hara in 2003 defines it as a functional on a topological set of knotted curves, satisfying that it's non-negative. And the second property, which is important, if two curves or two pieces of the curves come closer to each other and meet, then the energy must explode. This property is quite important for our applications, because if we have such a knot energy and let it continuously or let the curves flow continuously, then they cannot leave the knot class if the energy stays bounded. So in particular for gradient flows where we would like to dissipate this energy, it can't grow to infinity, so we stay in the same knot class. It has been shown for all the three examples I gave before that, well, these knot energies are in fact knot energies in this sense here. Well, O'Hara proved it for the O'Hara energies, and Simon Blatt and Philip Reiter showed it for these generalized tangent point and integral Menger curvature for, well, these various exponents. So for this talk, it will be important that these results, that this knot energy is repelling, are based on by-Lipschitz estimates for injective and arc length parametric curve. I will come back to this later in the proof of the main theorem. So the right topological spaces for these knot energies have also been found, well, again, by Simon Blatt and Philip Reiter in those three works. And these spaces are, if we start, okay, we have to put in that the curves are injective regular in the sense that the parametrization is not degenerate. And in this case, it turns out that the energy spaces, meaning the spaces for which the curves have finite energy, are exactly these Sobolev-Slobodetsky spaces. These are subspaces of the standard Sobolev spaces where another non-local semi-norm needs to be finite. So in this case, in all three cases, it is a subspace of Sobolev space with differentiability order 1, and we obtain this little s, and this s will of course then depend on these parameters pq and alpha. Okay, so now we can talk about gradient flows of knot energy. And the first gradient flows that were shown to exist were L2 gradient flows. First, Zheng Xu, he showed it in 2000 that the Mergus energy has, at least in short time, an L2 gradient flow. Simon Blatt then showed in 2012 and 2018 the long time existence. So by long time existence, we mean that we get a path of curves. So for every time t larger than 0, this flow is defined. And short time existence means that we only have, well, something like there exists a small interval, or maybe a large interval, but we don't know. There exists an interval on which the flow exists, and long time existence means it exists forever. Well, Simon Blatt showed that there is a true gradient flow of the Mergus energy for all times, given it starts sufficiently close to a local minimizer. Then for O'Hara energies with particular exponents, he shows the long time existence of L2 gradient flows if the functional is regularized with the length of gamma. So he adds to this O'Hara energy the length of the curve. This is important because, well, these energies, they are not scale invariant, in the sense that if you take a small curve and blow it up, then the energy decreases even if the the shape of the curve stays the same. So there will never be a minimum except a minimum with zero energy, because it can always blow the curve up to infinity, and then there is no meaning for this gradient flow. So this length of the curve is introduced to tackle this problem. He also showed that these gradient flows converge to a critical point. So we said the long-term existence means that the flow exists for all times, and then convergence means that in the limit time to infinity, this limit exists, and in this case, it's on these cases, it's a critical point. Then later on, the L2 setting was left, and people were more interested in, or also interested in gradient flows in the respective energy spaces. And so on this matter, I would like to mention Philipp Reiter and Henrik Schumacher, who took the Mergus energy and proved the short-term existence of the gradient flow in this metric related to the metric of the energy space. Then Jan Knappmann, Henrik Schumacher, Daniel Steenebrügge and Heiko von der Mosel proved the long-term existence of the gradient flow of the integral Menger curvature in the energy space, which in this case is a Hilbert space. And if we have P and Q equal 2, Daniel Steenebrügge in this dissertation then goes ahead and proves the long-term existence of the tangent point of the gradient flow of the tangent point energies. So this is useful because it leads to, at least in the case of the work of Philipp and Henrik, to more efficient and robust numerical methods compared with to the L2 flows. So in this talk, I would like to leave the Hilbert space setting and go into the Banach space setting. And to do this, I will briefly recall what actually a gradient flow in Hilbert space or Banach space is. In Hilbert space, if we take a smooth curve u and a smooth function of phi, then the gradient flow is this equation here, which should hold for every t, or maybe almost every t. And the gradient is in a Hilbert space, well, it's the Ries isomorphism inverted and then applied to the differential of the function. In Hilbert spaces, this Ries isomorphism is, well, in fact, a linear isomorphism. In Banach spaces, we kind of lose this property, and also it's unclear whether or not duality mapping, which replaces the Ries isomorphism, is still, well, if it's at least single valued. So in general, one could only hope for this kind of differential inclusion. And if the Banach space, in this case it's B, is nice enough, then the duality mapping is in fact invertible, or invertible, maybe also a homeomorphism. And yes, well, the duality mapping is given by this formula here. So we take elements of the Banach space and map it into the dual space, and we want to find those psi as such that satisfy this property here. And given a weight theta and the conjugate theta star, which satisfies this this exponent equality, and in the case where theta equals 2, then the Banach space is in fact a Hilbert space, we obtain back this Ries isomorphism. So the difficulty in so these are the difficulties when talking about gradient flows in Banach spaces. In our case, we have seen that the energy space or the Banach space would be a Sobolev-Slobodetsky space, these have nice convexity properties, so that in fact the duality mapping can be inverted, and we even know that it's a homeomorphism from the space, from the Banach space into its dual space. So we only have to consider this equation and no inclusion. However, we do not have that this thing is linear, and more importantly, maybe for our application, that it's not Lipschitz continuous. So now that I've talked about the gradient flows in Banach spaces, I would like to, well, introduce the energy we have studied in our work. And the energies are, well, the energies I used in your introduction as examples, namely the tangent point energies, the integral Menger curvature energies, and the O'Hara energies. And well, again, we faced the problem that the parametrization may blow up, so that the curve goes to or vanishes at infinity. So to circumvent this problem, we introduced a regularization, which will also play another important role in the existence of the gradient flow. Namely, we use this logarithmic strain in the work of Knappmann, Steenebrügge, Schumacher, and von der Mosel, which is the work on the existence of the gradient flow of the integral Menger curvature in the Hilbert space case. So when the exponent q equals 2 and the energy space is Hilbert space, they use this logarithmic strain and projected the gradient on the null space of the differential of this thing here. And this makes sure that the, oh, I'm sorry, here's a mistake, by the way. It should read gamma prime, so it's the derivative of gamma, which is also the reason why we lose here this little one. So, well, they project the gradient onto the null space of the differential of this logarithmic strain. And this has the property that, well, the parametrization stays fixed. So in fact, they show then, if you want, the existence of a gradient flow in a Hilbert submanifold. Here in our work here, we do not do this projection method. We just add the logarithmic strain in a norm. There's a question.
Yeah, just quickly, if I could, I'm intrigued by this logarithmic strain. So is there an interpretation of this as an entropy?
I'm not sure. So I was comparing it to the entropy for probability measures. So we tried to first do some kind of Wasserstein flow, and then this logarithmic strain seems a little bit like this entropy functional, like the Fisher entropy, but I'm not sure.
Yeah, I mean, if it was just a one-dimensional embedding, so thinking we get as a compressible material, then that would be the entropy of a compressible material. Just a curiosity, I've just puzzled. Thanks.
Mm-hmm. All right. So yes, we added the this energy or this penalty term, which is supposed to well, penalize all curves whose parametrization either grows too large or goes too close to zero, because the logarithm, or if we take the norm of it, it blows up in either of these cases. So this is the one part of the energy. When gamma is in fact in the energy space of the knot energy E. or if it's not, so if it fails to be either injective or regular, we set it brutally to plus infinity. Let me just say a couple of things about the constants here, or the parameters. There is this parameter kappa, which is here the exponent of this norm of the logarithmic strain. And this has the purpose, being larger than 1, that this part here is in fact differentiable. It was already shown that this logarithmic strain is differentiable. The norm of this Sobolev-Slobodetsky space is differentiable away from 0, because norms cannot be differentiable at 0. But when introducing this little kappa here, larger than 1, then the whole thing is differentiable. So, and the epsilon will play an important role in the existence proof. I will come back to it later, because here we slightly decrease the size of the Sobolev space in which the curve lives. And this is the purpose to allow for compact embeddings, which will also be needed later. That being said, we can now state our main theorem with the parameters as before. For every gamma naught in this Sobolev-Slobodetsky space, where S and rho are the corresponding parameters to the energy. So these will just be the energy spaces, which we have seen previously, plus this little epsilon. So for every gamma naught in this space here, there exists a curve or a path of curves, this capital board-face gamma, which is a C1 mapping, which exists for all time and maps into, well, again, the space here, such that it starts at gamma naught and satisfies this, well, this gradient flow or this Banach gradient flow equation with here this duality mapping with exponent theta, and it can be any theta larger than 1. Okay, so these three knot energies, they have a couple of things in common, and we will in fact only need these three properties to show that this gradient flow exists. The first one is the Fréchet differentiability, or the continuous Fréchet differentiability on their energy space, or this open subset of the energy space, the weak lower semi-continuity, and those by Lipschitz estimates I mentioned previously. And so now I will tell you what these are. Given a family of curves that are uniformly regular in the sense that this parameterization here, this gamma prime, cannot go arbitrarily close to 0 and cannot get as large as it wants. And if the energy of this family of curves is uniformly bounded, then, well, the bi-Lipschitz constant is also uniformly bounded from below, where this bi-Lipschitz constant is defined as the infimum of gamma y minus gamma x divided by x minus y in this distance on the circle. So this distance here is the distance on the circle. We take, if we have 2 points on the circle, we take the smallest arc connecting those 2 points, and this is then the distance. So all these properties have been shown to hold true in this work by Simon Blatt, Philipp Reiter, and Juno Hara, and except the continuous Fréchet differentiability of the O'Hara energy, which was done in our work in Theorem 5.1. So I can restate our main theorem and saying that we only need a knot energy satisfying those three conditions. So the continuous differentiability, the lower semi-continuity, or the weak lower semi-continuity, sorry, and this by Lipschitz estimate. Well, then this gradient flow exists as stated previously. The proof of this theorem will be done via minimizing movements and curves of maximal slope. So let me give you a very brief introduction into the concept of minimizing movements, curves of maximal slope. This is a generalization of gradient flows in Hilbert space to gradient flows in metric space. So let's say we have a smooth curve and a smooth energy in a Hilbert space, then this is the gradient flow equation. If you take or apply the Cauchy-Schwarz inequality, you can actually show that this here is equivalent to these two equations. From here to there, it's just put it in. And from here to there, we have, we have equality in the Cauchy-Schwarz inequality. So these two things have to be are linearly dependent. But we also know that they have the same size and we have the signs. So it actually, we obtain this equality here. And if we go one step further and use Young's inequality, we can even strengthen it to this inequality here. Again, from here to there, it's just inserted. And from here to there, it's equality in Young's inequality. And as a last step, we could say that, or we use the chain rule, because this thing here is nothing else than the derivative, the energy of this curve U, and then we get this inequality here. And so, why is this inequality important? Why did we do all this? Well, in this inequality here, we do not have any more linear structure. So we have the norm of the derivative, also the norm of the gradient, and here just derivative of the composed energy function, also no more scalar product. And this can be generalized to metric spaces. So instead of the norm of the derivative, we can introduce this metric derivative, where in our case, this metric D would be the metric induced by the norm of the Hilbert space. Same thing for the norm of the gradient. This would be replaced by the so-called local slope. And the third thing we need to generalize is the chain rule. Here is chain rule. And well, we lose this Hilbert space or this inner product. But what we can get is an inequality, kind of chain rule inequality, and that's called the upper gradient inequality. And using this, we can transform this energy dissipation inequality from the gradient flow case into the so-called curve of maximal slope case. And well, curve of maximal slope, they are just defined as those curves that satisfy these energy dissipation inequalities, which now make sense in metric spaces. And we can also go one step further and say that we integrate we integrate on a time interval and then get this integral energy dissipation inequality. So what we want to do is then show that such an energy dissipation inequality holds in our case. How is this done? I will briefly recall the existence theory for these curves of maximal slope, which is quite generally written down in the book by Ambrosio, Gigli, and Savary in the chapters 2 and 3. And I will briefly summarize it with our scenario in mind. So how do we get a curve of maximal slope using minimizing movements? In the first step, we fix a step size tau, strictly larger than 0, and solve an iterative minimization scheme. So given the curve gamma n-1, we look for the curve gamma that minimizes this functional here, which is again a kind of generalization of the implicit Euler functional for the gradient flow equation for metric spaces. And we do this, well, if we have gamma n minus 1, we minimize this, find a minimizer, and then do it again. So we start maybe at this quite edgy trefoil knot. In the first step, the edges are a little bit smoothed out, and then it gets even a little bit rounder. So this is the idea. And this leads to piecewise constant functions, gamma tau, where we just say that, well, between 0 and tau, it will be this one. Between tau and 2 tau, it will be this one. And between 2 tau and 3 tau, this one, and so on. And the important thing here is that, or the missing thing here is, well, I just said, well, we minimize this and find a minimizer, but it's not clear why this should exist. And this, in fact, was one of the major difficulties in the proof of our theorem. And so the approach, which is also given in this book by Ambrosi-Gilles-Savary, is to use the direct method of calculus of variation. We take a minimizing sequence, show that it's bounded, show that bounded sets are relatively or weakly relatively compact, and then use the lower semi-continuity of the functional. So the coercivity is quite clear for this functional here, because the energy phi is non-negative. Then we add a norm squared, so sublevel sets are bounded. We are in Sobolev-Slobodetsky spaces, which are reflexive. So bounded subsets are in fact weakly relatively compact. So the only thing missing here is the lower semi-continuity of the energy of this knot energy. I said that we kind of want this as an assumption of the knot energy, but there was a small detail here. We only have the weak lower semi-continuity on the set of injective and regular curves. So we do not know if I go back to the total energy, well, maybe I shouldn't do that. Okay, it will show later, sorry. Okay, let me then stay just here in this space here, injective and regular. By assumption, if we are here, the total energy, this phi here, is the knot energy plus this logarithmic strain term. And this thing here, by assumption, is weakly lower semi-continuous. This here is also because, well, this Sobolev-Slobodetsky norm is essentially, it's an integral with a non-negative integrand. So by Fatou's lemma, and we get the weak lower semi-continuity of this thing here. And the norm on these Sobolev spaces are also weakly lower semi-continuous. But the problem is, if we are not in the space of injective and regular curves, then by definition, the total energy is infinite. And then by extension, also this implicit Euler functional. And what might happen is that given a sequence of functions gamma k, which converge weakly to some gamma tilde, is gamma tilde then also injective and regular? Because if it's not, then, well, by definition of the total energy, the energy must jump to plus infinity, and this would break the lower semi-continuity. So this is the main part of the proof of the main theorem, and it is done by, well, combining by Lipschitz estimate from the knot energy, which holds by assumption, and using the fact that the logarithmic strain, when bounded in the Sobolev-Slobodetsky norm, implies that by embedding from this space into C0, that, well, the supremum of these derivatives is bounded. And since, well, we inserted into logarithm, we get the uniform regularity of these gamma tilde k's, in the sense that, well, this little C1 here exists. And so, well, one immediate consequence is that because we have this embedding into the space of continuously differentiable functions, we get from the weak convergence of gamma k to gamma tilde that we also have strong convergence in C1, and therefore applying this convergence to this inequality here, we get the regularity of gamma tilde. So it remains to show that gamma tilde is also injective. And as I said, we will use this by Lipschitz estimates because, well, if the total energy is bounded, then also the knot energy is bounded. And since we have these estimates here, and we have just shown that the norm of the logarithmic strain ensures this uniform regularity of the curves, we get these this uniform Lipschitz bound. And in particular, well, when passing to the limit again, gamma tilde is also injective, as otherwise we would this B Lipschitz inequality, or this B by Lipschitz constant of gamma k tilde would need to converge to 0. So in total, we have shown that if we have a family of curves with bounded energy that weakly converge to another curve, then it's injective and regular. And by assumption on the subset of injective and regular curves, the energy is weakly lower semi-continuous. So in total, well, the energy is weakly lower semi-continuous. And therefore, we can apply this machinery of direct method of calculus of variations and obtain this, can do this stepwise minimization scheme. So now it only remains to again follow what was done by Ambrosio Gilles-Savary in their book on gradient flows in metric spaces, namely pass the limit toward 0. In these cases, not just in our case, but in general, if you have these stepwise minimization functions, they satisfy this discrete kind of evolution energy dissipation inequality. And in particular, if we start at this, or we take the integral from 0, the whole thing is bounded by the energy of the starting point, and in particular the norms of the L2 norms of the derivatives are uniformly bounded, and then we can pass to, using Sela-Ascoli type of argument, we can pass to a subsequence and find a minimizing movement, which is by definition the limit of these piecewise constant curves. And in our case, this also works because we are also in the general metric setting. And as a last step, we want to show that this minimizing movement is in fact a curve of maximal slope and therefore a gradient flow. And this is the only place where this little epsilon comes into place, because, well, I just mentioned that these stepwise or this piecewise constant curve satisfy the discrete energy dissipation inequality. We have seen that these pass to a limit to a minimizing movement. And while we can also pass in this inequality to the limit, or this was done in Ambrosio Gilles-Savary's book, and we get that the limit curve satisfies this almost energy dissipation inequality, almost in the sense that, well, we have the metric derivative, we have the right values of the curve here at the time t and time 0. However, we do not have the local slope, but this relaxed local slope, which is the lower semi-continuous envelope of the local slope. So to show that this here actually is an energy dissipation inequality, our way is to show that this thing here is, in our case, actually the local slope. And well, this is the lower semi-continuous envelope. So we show that it is in fact lower semi-continuous. So then the EG envelope is just itself, the thing itself. And so the local slope was the norm of the gradient or the norm of the differential. And well, by assumption, the knot energy is C1. This thing here is also C1, so the total energy is C1. In particular, this thing here is continuous in the space 1 plus S rho. And by compact embedding, because we add a small epsilon here, this continuity extends to weak continuity. In particular, it's then also weakly lower semi-continuous. And so because this holds true, we can replace here this by the local slope, and we just get this energy dissipation integral inequality, which, well, is equivalent to the gradient flow. And that's pretty much it. So thank you for your attention.